So, why are we learning about formula masses? Well, it turns out that formula masses, a type of information that can be used in analytical chemistry labs to determine what an unknown substance is. So, when an unknown compound is brought into the lab, the percent composition of elements in that substance and its molar mass can be determined experimentally. The percent mass composition is then used to determine the empirical formula, and from the empirical formula and the molar mass, the molecular formula can be calculated. We're now going to learn how to find the empirical formula from percent composition. So let's say that we have a compound that's 30.4% nitrogen and 69.6% oxygen. What is the empirical formula for this compound? And we can figure it out just from the data we have here. First of all, we're going to assume that we have 100 grams of this compound, so we can convert percent to grams. So in this case, that would mean that we'd have 30.4 grams of nitrogen and 69.4 grams of oxygen, so that adds up to 100 grams. Why 100 grams? We could use another number, but 100 grams is nice, easy, because that way we don't have to do any math. We just convert the percent to grams. The next thing we do is convert the mass of each element to moles. So if we want a figure, basically if we want the formula, the grams, since nitrogen and oxygen have a different mass, that does not tell you what the ratio is going to be. But if we convert to moles, then we know basically the ratio of nitrogen and oxygen. So to figure out the number of moles, as we learned in the last lecture, we take the mass that we have and divide it to the molar mass, which is the mass in grams, basically grams per mole. And when we do this, grams cancels and mass divided by molar mass, and then we end up with moles on top. So this tells us how many moles there are. So we can do this for nitrogen. So we've got 30.4 grams because that's what we figured out. We assume that there's 100 grams, and we know that it's 30.4% nitrogen. So that's 30.4 grams that we have. And then the molar mass of nitrogen from the periodic table is 14. So we divide by 14 grams per mole. And then we end up with 2.17 moles of nitrogen. So that's how many moles we have. Now we'll do the same thing for oxygen. We have 69.4 grams in this unknown substance. Divide by 16 grams per mole, which is the molar mass from the periodic table. And we have 4.35 moles of oxygen. So now that we have these numbers, so in this substance, we've got 2.17 moles of nitrogen for every 4.35 moles of oxygen. Now we want to convert this essentially to a whole number ratio, because a compound is going to have always like a whole, it's going to have, you can't have half or a quarter of a nitrogen or oxygen atom. You have to have a whole number. So we got to figure out what the whole number ratio is from these two numbers. So to do that, we divide the number of moles of each element by the smallest number of moles present. What do I mean by this? Like, let's take the smallest number present. There's 2.17 moles of nitrogen, 4.35 moles of oxygen. So that means there's less nitrogen present. That's the smallest amount. So we're going to divide 2.17 by 2.17. That means that there's we make essentially 1 for nitrogen. And then we're going to do the same thing with oxygen. Divide, again, the smallest number of moles, which is 2.17. And then we're going to take the 4.35, which is the moles of oxygen, and divide it by that 2.17. And then we end up with 2. So we've got 1 nitrogen and 2 oxygens. So basically this tells us the ratio of elements in the compound. And then from that we can write the empirical formula. So that's going to be NO2. And if you remember from the previous lecture, the least electronegative element goes on the left, so nitrogen goes on the left, oxygen on the right. So it's NO2. Now this is the empirical formula. It could be N2O4 or something like a whole number. We could multiply and end up with a different number. We don't know if this is the molecular formula, but we do know that this is an empirical formula. So the smallest ratio that's present, so it's 2 oxygens for every nitrogen. Okay, let's do another example. So this time we're looking at a compound that contains 65.2% arsenic and 34.8% oxygen, and we want to know the empirical formula for this compound. So again, we're going to assume 100 grams because that's the easiest thing to do, and then we'll calculate the mass of each element. So basically we've got 65.2 grams of arsenic and 34.8 grams of oxygen. That's how many grams we have present for each. Now, again, we need to convert mass to moles, and this is going to give us an indication of the ratio in the absolute number of each of these. So again, we use the mass in grams divided by the molar mass in grams per mole to figure this out. So for arsenic, we've got 65.2 grams, and from the periodic table, we can see that arsenic has a molar mass of 74.9 grams per mole. So we end up, when we divide, with 0.871 moles of arsenic in this 100-gram sample. And for oxygen, it's 34.8 grams is how much we have, and oxygen has a molar mass of 16 grams per mole. We divide that, it's 2.18 moles of oxygen, again, in this 100-gram sample. So now to get basically the ratio, the formula, empirical formula for this, we're going to divide the number of moles of each element by the smallest number of moles present. So we look at these, there's less arsenic, 0.871 moles, than there is oxygen, 2.18. So this arsenic is going to be the lowest number, so that's the one we're going to use to divide. So for arsenic, it's going to be 1. So whichever is the smallest number present, that's always going to have a ratio of 1 because we're dividing it by itself, essentially. And then we're going to look at oxygen. So again, we're going to divide by 0.871. So we're dividing both by the same. We want the same ratio, but we want it to. What we're trying to do here is essentially we have a ratio of 0.871 moles to 2.18 moles, but we want to make this a whole number ratio, and this is a way of doing it. Dividing by 0.871, we know that we're going to have a whole number ratio for arsenic, and we also hopefully will for oxygen. However, if we look here, it didn't quite happen. So we have 2.18 moles to 0.871, which gives us a value of 2.5. So in other words, there's 2.5 oxygens for every arsenic. Now we can't have half an atom, so what we have to do is double this. What we when we start out with, but for our empirical formula, we're going to double. So it's AS2O5. Now, when you do these, you should always eventually be able to end up with a whole number ratio, and if it is a compound, that's always going to happen. And if you don't end up eventually with a whole number ratio or something that's like exactly half, so you can double it to get whole, there's probably something wrong with your calculation because you should end up with a whole number ratio. Okay, we're going to do another example, and this one's a little bit trickier because we don't have just 2 elements. We have a molecule that actually has 4 different elements in it: carbon, hydrogen, nitrogen, and oxygen. So again, we're going to just assume that we have 100 grams total, and so basically the grams of each substance adds up to 100, or of each atom. And now we're again going to convert the mass of each element to moles, and we have to do that to figure out the relative number of each element. So basically, for carbon, we've got 63.5 grams. And then we're going to multiply that times, we're essentially dividing by the molar mass, or multiplying times 1 over the molar mass. So we have 63.5 grams, and that's times 1 mole divided by 12 grams, and that's going to be 5.29 moles. And then for hydrogen, it's 1 mole per 1 gram, so that's 6 grams to start, so we're going to end up with 6 moles. For nitrogen, there's 9.27 grams, and nitrogen is 14 grams per mole, so we divide by 14 and end up with 0.66 moles. And for oxygen, there's 21.1 grams, divide by 16 and end up with 1.32 moles. So the next thing we're going to do is, again, it's just the same as we did before. We're going to divide the number of moles of each element by the smallest number of moles present. So if we look at this, nitrogen, there's less moles of nitrogen than anything else. So this is going to indicate that there's less nitrogen than there is the other atoms present, but we need to figure out exactly how much left is less in a whole number ratio. So we're going to divide by for nitrogen, 0.66 by 0.66. So that gives us 1 nitrogen. And then we're going to divide everything else also by 0.66. So that gives us 8.01 for carbon, 9.09 for hydrogen, 1 for nitrogen, and 2 for oxygen. So notice here that it's not exactly 8 or 9. We have 8.01 and 9.09, but in this case we are going to round off, so that is probably just a measurement error or a rounding error that happens, but you have to have a whole number ratio. It's not possible to have 8.01 carbon atoms, so we know that it's 8. So basically, this is the empirical formula for this: C8H9NO2.